Let me tell you something that Hollywood doesn't want you to know. Something that science fiction writers ignore. Something that optimistic futurists dismiss as mere engineering challenges. Interstellar travel, sending humans to other star systems, is not just difficult. It's not just expensive. It's not just beyond our current technology. It's impossible. Fundamentally, physically impossible. I don't mean impossible in the sense that people once thought heavier-than-air flight was impossible, or that they thought we'd never reach the moon. I mean impossible in the sense that perpetual motion machines are impossible, in the sense that traveling faster than light is impossible, in the sense that the laws of physics themselves forbid it. After 50 years of thinking about physics, of working on relativity and quantum mechanics and cosmology, I've come to accept a hard truth. We are stuck here, on Earth, in our solar system, maybe eventually spreading throughout the Oort cloud, but the stars, the thousands of potentially habitable exoplanets we've discovered, they might as well be in different universes. Let me show you why, and I'm going to be precise about this. No hand-waving, no appeals to future technology we can't imagine, just physics. Hard, cold, unforgiving physics. The fundamental problems are distance, energy, time, and biology. Each one alone is nearly insurmountable. Together, they form an absolute barrier. Let's start with distance, the problem of distance. The nearest star system to Earth is Alpha Centauri, about 4.37 light-years away. That's roughly 41 trillion kilometers. To put this in perspective, if Earth were the size of a grain of sand, Alpha Centauri would be 40 kilometers away. Voyager 1, our fastest spacecraft, is traveling at about 17 kilometers per second relative to the Sunday. At that speed, it would take about 75,000 years to reach Alpha Centauri. That's not a typo. 75,000 years, longer than all of recorded human history. And Alpha Centauri is the closest star. The average distance between stars in our galaxy is about 5 light-years. Most interesting exoplanets we've found are hundreds or thousands of light-years away. Kepler 186f, one of the most Earth-like exoplanets discovered, is 500 light-years distant. At Voyager's speed, reaching it would take more than 8 million years. Now, you might say, well, we just need to go faster. And yes, that's obviously true. But here's where the physics gets brutal. Let's imagine we want to make the trip to Alpha Centauri in a human lifetime, say, 50 years. That means we need to travel at about 10% the speed of light. That's 30,000 kilometers per second, about 1,800 times faster than Voyager. Can we do that? Let's look at the energy requirements. The energy problem. The kinetic energy of a moving object is 1/2 mass times velocity squared. At low speeds, this is manageable. But at 10% the speed of light, you need to use the relativistic formula, which is even worse. Let's be conservative and assume we're sending a small spacecraft, say 1,000 kilograms. That's tiny, barely enough for one person and minimal life support. No fuel, because we'll calculate that separately. The kinetic energy needed to accelerate this 1,000 kilogram spacecraft to 10% light speed is about 4.5 times 10 to the 17th joules. That's 450 petajoules. How much energy is that? The entire world's energy consumption in 2023 was about 600 exajoules. That's 600 times 10 to the 18th joules per year. So accelerating our tiny spacecraft would consume about 1/10,000th of a year's worth of all human energy production. That's the energy output of all human civilization, every power plant, every car, every light bulb running for about 50 minutes, just to accelerate the spacecraft. You still need to slow it down when you arrive, which takes the same energy again, so double that. An hour and 40 minutes of all human energy production for a 1,000 kilogram spacecraft, a payload smaller than a compact car. Now let's talk about the fuel. If you're using chemical rockets, the best we have, the energy density is pathetic. Gasoline contains about 46 megajoules per kilogram. Even hydrogen-oxygen rockets, which are better, give you about 13 megajoules per kilogram. To get 450 petajoules from chemical fuel, you'd need about 35 billion kilograms of fuel. That's 35 million metric tons. For comparison, the International Space Station has a mass of about 450 metric tons. Your fuel alone would be 75,000 times more massive than the ISS. And remember the rocket equation. The more fuel you carry, the more mass you have to accelerate, which means you need more fuel, which means more mass, in an exponential spiral. When you do the calculation properly using the Tsiolkovsky rocket equation, you find that chemical rockets simply cannot reach 10% light speed. The fuel-to-payload ratio becomes astronomical. You'd need a fuel mass many times greater than the mass of the observable universe. So chemical rockets are out. What about nuclear propulsion? Nuclear fission releases about 80 trillion joules per kilogram of uranium. 235. That's about 1,000,000 times better than chemical fuel. Nuclear fusion, if we could make it work, efficiently releases about 600 trillion joules per kilogram of fuel. Let's use fusion, since we're being optimistic. To get 450 petajoules, you'd need about 750 kilograms of fusion fuel. That's actually manageable. Add another 750 kilograms for deceleration, and you're at 1,500 kilograms of fuel. So the total mass of your spacecraft payload plus fuel would be 2,500 kilograms. Much better. But there's a problem. Converting fusion energy into directed thrust is hard. Really hard. Current fusion reactor designs, like ITER, are massive and inefficient. They require huge magnetic coils, cooling systems, and structural support. The reactor mass dwarfs the fuel mass. Even if we imagine a breakthrough in fusion propulsion, a lightweight, efficient reactor, we face another problem. You're not just accelerating fuel. You're accelerating the engine, the structure, the radiation shielding, the payload. Every kilogram of additional mass requires more fuel. And speaking of radiation shielding, a fusion rocket creates intense neutron radiation. The crew compartment needs heavy shielding. Water, lead, polyethylene all add mass. Kilograms of shielding for every kilogram of payload. When you account for all of this realistically, the mass ratios become prohibitive again. We're back to needing many times the payload mass in fuel and structure. But let's keep being optimistic. Let's imagine we solve all of this. Let's assume perfect fusion drives with nearly 100% efficiency and minimal mass overhead. Can we finally make the journey? Not quite, because there's another energy problem, interstellar dust, the dust problem. Space is not empty. Even the near vacuum of interstellar space contains about 1 atom per cubic centimeter, mostly hydrogen. At low speeds, this is negligible. But at 10% the speed of light, you're hitting about 3 times 10 to the 13th hydrogen atoms per square meter per second. Each collision transfers energy. At 10% light speed, each hydrogen atom hits with a kinetic energy of about 5 kiloelectron volts. That doesn't sound like much, but multiply by trillions of atoms per second hitting every square meter of your spacecraft's cross-section. For a spacecraft with a frontal area of just 10 square meters, very small, you're absorbing about 2.4 megawatts of power continuously. That's like having 2,400 1-kilowatt heaters running constantly on the front of your ship. This energy turns into heat, it ablates the hull, it creates secondary radiation, you need shielding which adds mass, which requires more fuel, which makes the problem worse, and hydrogen atoms are the least of your worries. There are also dust grains, tiny particles, mostly carbon and silicates, averaging about a micrometer in size. There's roughly 1 such grain per 1,000 cubic kilometers. At 10% light speed, a 1 microgram dust grain hits with the kinetic energy of about 45,000 joules. That's equivalent to 10 grams of TNT. Every grain punches a hole through your spacecraft like a hypervelocity bullet. Over a 50-year journey, your spacecraft will sweep through a volume of about 20 trillion cubic kilometers. That's 20 billion potential impacts. Even with the sparse distribution, you're looking at millions of grain impacts. You need shielding, heavy shielding, or a massive magnetic field to deflect charged particles. Both add mass, both require energy, both make the mission harder. We're accumulating problems, but it gets worse. The time problem. Even if we could somehow solve the energy and shielding problems, even if we had magical propulsion systems that violate everything we know about engineering, we face the problem of time. A 50-year journey to Alpha Centauri means 50 years on the spacecraft. But who's going to sign up for a one-way 50-year journey to a star system we've barely studied? You might think, well, we'll put people in suspended animation or cryogenic sleep. This is not technology. This is fantasy. We cannot freeze and revive humans. Every cell in your body contains water, and water expands when it freezes, rupturing cell membranes. The damage is catastrophic and irreversible. Some researchers are working on inducing hibernation-like states through metabolic suppression. Maybe, and this is a big maybe, we could slow metabolism by a factor of 10. That would make a 50-year journey feel like 5 years to the crew. Still half a decade of their lives spent in a tiny spacecraft. And here's the darker problem. What happens on Earth during those 50 years? Technology advances. If we can barely send a spacecraft at 10% light speed in, say, the year 2100, what will be possible by 2150? Probably 20% light speed, or 30%. So you launch your crew in 2100, they arrive at Alpha Centauri in 2150, but a faster ship launched in 2125 arrives in 2140. Your crew spent 50 years traveling to a destination that was already reached by others who left later. This is called the weight calculation, and it creates a perverse incentive. It's always better to wait for better technology than to launch with current technology. Unless you know your technology is close to the theoretical limits, which brings us back to the speed of light, and that's the ultimate time problem, relativity. The relativity barrier. Let's say we want to make interstellar travel reasonable, a few years of trip time subjectively for the crew. To do this, we need to approach the speed of light closely, say 90% of light speed. At 90% light speed, time dilation becomes significant. Gamma factor is about 2.3. This means for every year that passes on the spacecraft, about 2.3 years pass on Earth. A trip to Alpha Centauri at 90% light speed would take about 4.9 years Earth time, but due to time dilation, the crew would experience only about 1 years. That's manageable, but the energy requirements become insane. The relativistic kinetic energy of a 1,000 kilogram spacecraft at 90% light speed is about 5.8 times 10 to the 19th joules. That's 58 exajoules. Almost 10% of annual global energy production for a 1,000 kilogram payload. To accelerate 1,000 kilograms to 90% light speed using fusion fuel at 100% conversion efficiency, you'd need about 96,000 kilograms of fuel. 96 tons of fuel for every ton of payload. And the radiation problem gets worse. Those hydrogen atoms, at 90% light speed, each one hits with about 430 kilo electron volts. Your spacecraft is now absorbing about 200 megawatts of power from interstellar hydrogen collisions. That's the output of a small nuclear power plant concentrated on the front surface of your ship. The dust grains become relativistic missiles. A 1 microgram grain at 90% light speed hits with 5.8 million joules. That's more than a kilogram of TNT. Each grain impact is an explosion. You'd need shielding meters thick, made of the densest materials, adding thousands of kilograms of mass, requiring millions of kilograms of fuel. And we haven't even talked about what happens when you want to stop. The deceleration problem. You've accelerated to 90% light speed. You've somehow survived the radiation and dust impacts. You're approaching Alpha Centauri. Now you need to slow down. If you don't slow down, you'll zip through the system at 270,000 kilometers per second. The entire star system will flash by in hours. You won't be able to orbit. You won't be able to land. You'll just keep going into the void. So you need to decelerate, which requires the same energy you use to accelerate. Another 58 exajoules, another 96 tons of fuel per ton of payload. But here's the problem. You had to carry that deceleration fuel with you the entire journey, which means you had to accelerate it at the beginning, which means you needed more fuel to accelerate the fuel you need to decelerate. The rocket equation strikes again. When you do the math, the fuel requirements spiral to absurdity. You need thousands of tons of fuel to carry hundreds of tons of fuel to slow down a spacecraft, carrying tens of tons of fuel to slow down a spacecraft with 1 ton of payload. Some proposals suggest using magnetic scoops to collect interstellar hydrogen during the journey and use it as fuel. The Bussard ramjet, proposed in 1960. Beautiful idea, doesn't work. The problem, the drag from collecting the hydrogen creates more deceleration than you gain from burning it. You actually slow down. The numbers don't work out. Robert Zubrin and Dana Andrews proved this in the 1990s. Other proposals. Laser sail, pushed by Earth-based lasers for acceleration, then deploy a magnetic sail for deceleration using the star's stellar wind. Clever, but the engineering is fantastical. You need lasers with petawatt power levels. You need sails thousands of kilometers across. You need perfect stability and control over light-year distances. We're leaving physics and entering fantasy. The biology problem. Let's pretend, for the sake of argument, that we solve all the physics and engineering problems. We have a spacecraft that can reach Alpha Centauri in a few years, ship time. Can we actually send humans? No. Because biology, cosmic radiation is the killer. Outside Earth's protective magnetic field and atmosphere, you're exposed to galactic cosmic rays and solar energetic particles. These are high-energy protons and heavy ions that pass through spacecraft walls like they're not there. On the International Space Station, astronauts receive about 150 millisieverts of radiation per year. That's about 50 times more than you'd receive on Earth's surface. For a 6-month mission, this is acceptable. It increases cancer risk slightly, but remains within safety guidelines. But an interstellar journey, even a short one of 5 years, you're looking at 750 millisieverts minimum. Probably much more, since you're traveling through interstellar space far from the sun's heliosphere, which provides some shielding. At these doses, you're significantly increasing cancer risk. Cataracts become likely, radiation sickness is possible, and we don't fully understand the long-term neurological effects of cosmic ray exposure to the brain. The only way to shield against cosmic rays is mass. Meters of water, lead, or polyethylene, thousands of kilograms per person, which we're back to the mass problem, the fuel problem, the energy problem, and cosmic rays are just one issue. There's also bone density loss in microgravity, about 1 to 2% per month. After a year, astronauts have osteoporosis level bone density. We can mitigate this with exercise, but not eliminate it. Muscle atrophy. Even with rigorous exercise, astronauts lose 20 to 30% of muscle mass on long missions. Vision problems. Many astronauts develop vision changes due to fluid shifts in microgravity. The mechanism isn't fully understood. Immune system suppression. Extended spaceflight weakens immune function, making infections more dangerous. Psychological issues. Isolation, confinement, monotony, distance from Earth all take psychological tolls. ISS astronauts are in constant contact with Earth and can return in hours if needed. An interstellar crew would be years from home with no possibility of rescue. Some of these problems could be solved with rotating spacecraft to create artificial gravity, but rotation adds engineering complexity. It adds mass. It requires structural strength. The rotating section needs to be large, at least 100 meters radius, to avoid disorienting Coriolis effects. We're back to the mass problem, the energy problem, the impossibility, generational ships. Maybe you think we don't send people for a few years, we send them for generations. A generation ship, a massive habitat carrying thousands of people who will live, reproduce, and die during the centuries-long journey. This is not physics anymore. This is sociology, ecology, genetics, and psychology. And the problems are staggering. You need a closed-loop life support system. Perfect recycling of air, water, and nutrients for centuries. We cannot do this. Our best closed system experiments, Biosphere 2, for example, failed to maintain balance even for years. You need genetic diversity. A founding population of at least several hundred people to avoid inbreeding, probably thousands for long-term viability. You need social stability. Your ship is a dictatorship. There's nowhere to escape if society breaks down. How do you maintain order, culture, purpose across generations of people who never chose to be there? You need redundancy in critical systems. If the water recycling fails, everyone dies. If the power system fails, everyone dies. You need backups, spares, repair capabilities for systems we barely understand for centuries without resupply. The mass of such a ship would be millions of tons. The energy to accelerate it would be, I don't even want to calculate it, a significant fraction of all the energy humans have ever produced. And for what? To send a few thousand people to a star system decades or centuries away, where they'll arrive as technological primitives compared to whatever Earth has developed in the meantime. Assuming Earth hasn't collapsed, or humanity hasn't gone extinct, or we haven't discovered faster than light travel, spoiler, we won't, that's even more impossible. Generation ships are fantasy, appealing fantasy for science fiction, but fantasy nonetheless. Alternative destinations, you might argue, okay, interstellar travel is impossible for humans, but what about probes, small robots? Yes. This is much more plausible. The mass is lower, the energy requirements are manageable, and robots don't care about radiation or time. The Breakthrough Starshot project proposes exactly this. Centimeter-scale spacecraft with light sails, accelerated to 20% light speed by ground-based lasers. Trip time to Alpha Centauri, about 20 years. The physics works, barely. The engineering is extraordinarily challenging, but not impossible. The energy requirements are huge, but conceivably achievable with globally coordinated effort. But these are probes. Not colonization, not human expansion. They'd send back pictures, data, measurements. Wonderful for science, useless for establishing a presence. And they're one way. At 20% light speed, there's no slowing down. They flash through the Alpha Centauri system in days, cameras clicking, then they're gone forever into the void. Or you might argue, what about the solar system? Mars? The moons of Jupiter and Saturn? Yes, these are reachable, difficult, expensive, requiring centuries of technology development, but not impossible. Mars is 7 months away, the moons of Jupiter a few years. Even the outer solar system is reachable within decades. We could plausibly establish permanent settlements on Mars, underground habitats on the moon, mining operations in the asteroid belt, research stations on Titan or Europa. But this is not interstellar travel, this is staying home. Alpha Centauri might as well be in another dimension for all the good it does us. The Fermi paradox solution. Here's what I think the physics of interstellar travel tells us about the Fermi paradox. Enrico Fermi famously asked, where is everybody? If intelligent life is common, why don't we see evidence of other civilizations? Many solutions have been proposed. Maybe life is rare. Maybe intelligence is rare. Maybe civilizations destroy themselves. Maybe they're hiding. Maybe they're here and we don't recognize them. But there's a simpler answer. Interstellar colonization is impossible. Every civilization that evolves, regardless of how technologically advanced they become, hits the same wall we're hitting. The physics is universal. Energy requirements scale the same way. The speed of light is the same everywhere. So civilizations arise, they spread through their solar systems, and then they stop because the stars are too far away, too expensive to reach, too dangerous to travel to. We're alone not because we're special or first or doomed We're alone because everyone is alone, trapped in their own solar systems by the tyranny of distance and the conservation of energy. This is the solution to the Fermi paradox that physics suggests, and it's probably correct. The philosophical implications: what does it mean if we're truly stuck here, if the stars are unreachable, not just now, but forever? It means Earth and our solar system are all we get. This is it. This is humanity's domain. About 10 to the 13th cubic kilometers of usable space, if we're generous, and include the entire volume of the solar system out to the Kuiper Belt. It means the exoplanets we're discovering, the Earth-like worlds orbiting other stars, are forever beyond our reach. We can look, we can measure, we can dream, but we can never go there. They're dead to us. It means the long-term future of humanity is tied entirely to the sun's lifespan and the resources of our solar system. We have about 1 billion years before the sun's luminosity increases enough to make Earth uninhabitable. Maybe 5 billion years before the sun becomes a red giant and swallows the inner planets. That's a long time. Plenty of time for humanity to flourish, evolve, transform into something unrecognizable. But it's finite, and it's local. It also means we need to be more careful with what we have. If Earth is not just our home, but our only possible home, if there's no backup planet we can flee to, if we destroy this one, then preservation becomes paramount. Climate change, nuclear war, ecosystem collapse, artificial intelligence, risks. These aren't just threats to our current civilization. They're threats to the only civilization that can ever exist in this corner of the galaxy. Some people find this depressing. I find it clarifying. It focuses the mind on what matters. We have one planet, one solar system, one chance. We should make the most of it. Could I be wrong? Let me address the obvious question. Could I be wrong about interstellar travel being impossible? Of course. I've been wrong before. Every physicist has. The history of science is full of confident pronouncements that turned out to be false. Lord Kelvin said heavier-than-air flight was impossible. Nuclear physicist Ernest Rutherford said extracting energy from atoms was moonshine. Astronomer Royal Richard Woolley said space travel was utter bilge. They were all wrong, so maybe I'm wrong too. But here's the difference. Those predictions were based on limited understanding or imagination failures. They didn't account for new physics or engineering breakthroughs. My argument is based on fundamental limits. The speed of light is not a technological limitation. It's a feature of space-time itself. Energy conservation is not an engineering challenge. It's a law of nature. The distances between stars are not a temporary obstacle. They're a geometric fact about the universe we inhabit. Could there be loopholes? Could we discover new physics that allows faster-than-light travel? Wormholes? Warp drives? Exotic matter with negative energy density? These appear in general relativity's equations as mathematical possibilities, but they require things we've never observed and have good theoretical reasons to think don't exist. Wormholes require exotic matter with negative energy density in quantities that exceed anything quantum field theory allows. Warp drives require similar exotica, plus the ability to manipulate space-time curvature on macroscopic scales with energies exceeding the mass energy of planets. These are not engineering challenges. They're demands for physics that violates everything we know. Could we be missing something fundamental? Sure. Maybe quantum gravity will reveal new possibilities. Maybe there are extra dimensions we can shortcut through. Maybe consciousness can transcend space in ways we don't understand. But betting on unknown physics to save us from known physics is not rational. It's wishful thinking. The smart money says, interstellar travel is impossible. Act accordingly. Conclusion. I know this is not what you wanted to hear. Science fiction has trained us to expect Star Trek, Star Wars, galaxies full of civilizations, trading and warring and exploring. But science fiction is fiction. Physics is reality. And physics says the stars are too far away, the energy requirements too extreme, the dangers too great, the timescales too long. We are islanders in a vast ocean. We can see other islands on the horizon, those exoplanets orbiting distant stars. We can study them with telescopes. We can wonder what's there, but we can never visit them. Our island, the solar system, is large enough for a very long future. We can build habitats throughout it. We can use the sun's energy for billions of years. We can create a rich, complex, enduring civilization. But we'll do it here, alone, without ever touching another world that orbits another star. That's what physics tells me. And after 50 years of listening to what physics says, I've learned to trust it. The universe is beautiful and vast and full of wonders, but most of those wonders are beyond our reach, and we need to accept that. We're home. We've always been home, and we always will be.